Welcome everyone to another live session for the Astronomy online course. This actually will be the last for a month because I'm going to Italy this weekend to teach at the Vatican Observatory Summer School, which is actually a lot of fun. Being in Italy is always fun, and these are 24 of the brightest young students from around the world that are learning astrophysics for the first time. The subject is actually water in the universe. So the floor is open for your questions.
All right, so our first question is, a consequence of inflation theory is that it predicts many universes in which the laws of physics are different. How can this be called a prediction?
Right, it's a fair criticism, and I think it's even being overly generous to the inflation theory to say that it predicts many universes. The multiverse hypothesis or concept is not an automatic and necessary or absolute consequence of inflation. Inflation itself is just a mechanism through a field that's generated early in the universe, probably from some form of unification of gravity and the other forces, that exponentially inflates the universe by 42 e-foldings, roughly, from far smaller than the size of a proton to something like the size of a grapefruit or a meter or so. That mechanism can be postulated without reference to multiple universes. So these two things are often connected in popular science literature, but I don't think they actually should be, because you need a more profound underlying theory to predict what the inflation field results from. And it is only one possible set of theories that results in space-time fluctuations and the possibility of other universes unobservable by us. So I will separate then the idea of inflation, for which there is some observational support, and a mechanism which is rooted in, not physics that isn't understood, but physics that is at the speculative edge of current particle physics theories, from the multiverse theory, where we really have no theoretical basis for predicting what the ensemble of universes in the multiverse would be. So that's really moving out on the limb of speculation. But for people who choose to do so, and the people working on this theory, indeed it's possible that the same fluctuating field that results in inflation of our universe could result in other patches of space-time with completely different properties, some of which inflate, some of which don't inflate, in which the laws of physics exist but are quite different from in our universe. And that, of course, leads even further down the road of speculation to anthropic ideas, but I'm not going to go there.
All right, the next question is from David via email. I'm puzzled by all the events that are said to occur in the first tiny fraction of time after the Big Bang. For example, the formation of baryons from quarks and gluons at 10 to the minus 6 seconds. Surely all the particles and photons, even traveling at or near the speed of light, just would not have time to undergo so many changes in such a short time.
So it's a good question, because the idea of equilibrium, in the sense of thermal equilibrium, where everything has the same temperature, is part of the reason the inflation idea was postulated. When we look, we don't even have to go back to the first tiny fractions of a second. When we look at the microwave radiation left over from the Big Bang, the CMB, that dates from 380,000 years after the Big Bang, a time when stable atoms formed, when the temperature was about 3,000 Kelvin. And different patches of the sky, looking in different directions, at that time in the early universe, those regions were moving away from each other at something like 40 or 50 times the speed of light. So they should not have the same temperature, which they do, to 1 part in 10 to the 5. So we have an equilibrium problem there, and inflation was designed to explain that by saying that all of the patches of sky that we see across the sky in the microwave background represent a tiny pre-inflation patch of space-time that was expanded to encompass the size of the observable universe now. When we go back before these eras, we are not dealing with equilibrium physics, but still there is continual interchange between energy and mass by equals mc squared. And so probably the biggest landmark where our physics is still rooted in well-known standard model of particle physics theories is the first microsecond, when we believe the great imbalance between baryons and antibaryons, the lack of antimatter in our universe, first originated. And so that was the time at which particles and antiparticles were in equilibrium with each other and with radiation, but a tiny asymmetry existed between the particles and antiparticles, obviously in favor of the things we choose to define as particles. And then when that final annihilation occurred, it left the universe flooded with radiation with a tiny little residue of matter, basically one part in a few times 10 to the 8. So that physics is fairly well understood. Anything before that is pretty much in the realm of speculation, because we don't know what dark matter is, we don't know what dark energy is, and so we can't even speculate what the particles might be that exist in the even earlier universe that would have been exchanging or coming and going out of pure radiation.
All right, our next question is from Chris. Actually, I am fascinated about the Atacama Specialized Planet Hunter Telescope that just found 3 habitable zone planets circling a red dwarf star only 40 light years away. Can you please explain the difference between a red dwarf and our own sun Sol?
Yeah, the planet hunting game has obviously moved very rapidly and was focused initially, perhaps even for the first 15 years, on sun-like stars and then eventually getting down to Earth-like planets. But it's been realized in the last 5 to 8 years that the amount of habitable real estate in the Milky Way or in the universe around dwarf stars actually exceeds the amount of habitable real estate around sun-like stars. So dwarf stars are obviously far less luminous, hundreds to thousands of times less luminous than the sun. And if they have planets and habitable zones, those zones will be shrunk much closer to the star and actually be quite slender. But there are so many red dwarfs per sun-like star, thousands, that you multiply that up and you find out there's more habitable real estate in the red dwarfs. So people realized it was kind of inappropriate to limit the search for planets and even Earth-like or habitable planets to sun-like stars. And so now large surveys have started to look for planets around dwarfs. There's another advantage of looking for planets around dwarfs, which is, of course, that the star itself is a couple of orders of magnitude dimmer. So if you are trying to do the very difficult job of detect the planet directly by its reflected light, you're fighting against a much less luminous star, which you still have to suppress that stellar radiation to see the reflected light of the planet. But that's a slightly more tractable issue. That advantage, of course, is offset a little bit by the fact that the planet, to be habitable, is going to be closer to the red dwarf than a Earth-like planet will be to a sun-like star. So you're having to remove the star, but the planet is tucked in very close to the star. Nonetheless, as people have looked for planets around red dwarfs, they found them at essentially the same frequency that they find them around sun-like stars, and so the game has essentially opened up. The reason that you go in that direction and not the other direction is that the more luminous stars than the sun have shorter lifetimes, main sequence lifetimes, and by the time you're 2 times the mass of the sun, you have a star that lives less than 1 billion years on the main sequence, which may not be long enough for a complex life to form on an Earth-like planet. Whereas the dwarfs live extremely long times, tens or hundreds of billions of years. So not only is there the possibility of habitability, but there's a long, stable phase of main sequence fusion for which life could be supported.
Right, the next question is from Richard. Is it possible that space is like any other particle in the universe with properties that are in common with all particles?
It's certainly indeed appropriate to think of space as a medium which shares some properties with particles, because in standard physics, we know that particles and antiparticles can come in and out of being out of empty space, out of the pure vacuum. So in that sense, space is a sort of latent medium for the creation of particles and antiparticles, or pure energy. The nature of what space is, empty space is still up for discussion, because the vacuum in physics is actually a very rich medium. It's not empty, it's full of sort of latent possibility. So it is true that the sort of distinction between space as an empty container and the particles that sit within the space has been melted away a little bit by modern physics. Now, what is the nature of space fundamentally? If you observe the finest grain of space, then string theory would predict that at some point space is grainy, that it's fundamentally quantized, that it does not exist as a smooth and continuous medium. And at that point, you really are starting to look at something that's a little bit more like particle nature. But string theory is, of course, an unproven topic. So, but that is where the theory is tending. So in that sense, yes, space is moving towards having particle-like properties, if you think of it in terms of string theory.
All right, Stephen, who is on with us live, asks, will the CMB, the cosmic microwave background, fall over the visible horizon?
The horizon concept, I'm not quite sure I understand the intention of the question, but the CMB essentially represents the limit of our vision. It's the epoch in the universe early on, in the very first fraction of a percent of the universe's history, when stable atoms formed and radiation could travel freely. So it represents the opacity of the universe looking backwards in time. The CMB is within our horizon because we observe it in every direction in the sky. So those microwave photons exist and they fill space, and we see them back to a redshift of about 1080 actually, which is that fraction of a percent since the time of the Big Bang. So they are all within our horizon. What is going to happen, however, and maybe this was a sense of the question, is that in the future of the accelerating universe, space-time is going to expand at an accelerating rate. And if you project that very far into the future, especially if it's a sort of an exponential trend, eventually those microwave photons that have already been stretched from sort of dull red photons at a redshift of 1,000 to microwaves at the current epoch will gradually stretch to the point where they leave our horizon. In other words, the energy and the temperature of the microwave background will reduce to tiny fractions of a Kelvin, and the wavelengths will actually reach the point of leaving our horizon or our sphere of visibility. So that is a logical extrapolation of the expansion of the universe into the far future. How far? A little hard to tell because we don't know the properties of dark energy very well, but we're probably talking tens of billions of years in the future when the CMB, as the question implied, will indeed leave our horizon.
Roger, Roger via email asks, why does the sun spin differently at the equator than at the poles? I would think slower at the equator because it's bigger.
The sun is a plasma ball with angular momentum, so it has a net rotation. But there are essentially viscous forces that operate within the sun because it's threaded by a magnetic field. So because it's charged particles, there are electric and magnetic stresses and forces that operate on the sun, and they act as a sort of drag. So the slower regions and the faster regions are coupled, and they affect each other. And that coupling is accentuated by the magnetic field that threads the sun, because as the sun passes through the points of its solar cycle, those magnetic field lines get stretched, and there's magnetic tension associated with the twisting of the magnetic field lines, and they're winding up, if you like, from the fast rotation of the equator. So describing how the sun actually rotates is not as simple as taking a big ball of hot gas, because it has to be a sort of magneto-hydrodynamic calculation done in 3 dimensions. And actually the sun is well enough understood that those models work pretty well and explain what we see in terms of the sun's rotation.
Victor via email asks, black holes do not emit light, but they do emit heat, neutrinos, but do they emit heat, neutrinos, or any other type of radiation? And does this heat from, this is a separate question, I'm sorry, do they emit any kind of radiation?
Yeah, so black holes are hypothesized. Now, this is not confirmed by observation yet. This is, of course, theories from Stephen Hawking in the late 1970s and others, Bekenstein in particular, who died recently and was duly feted by physicists because he's one of the more famous and esteemed physicists on black hole theory that most members of the public haven't heard of. Everyone knows Stephen Hawking. Not too many people knew Jacob Bekenstein, but they worked together on a lot of stuff, and Bekenstein was a brilliant theorist. So Hawking and Bekenstein hypothesized that beyond angular momentum and mass, a black hole actually did have a temperature. And so there is radiation, extremely feeble radiation that comes off a black hole. And this is basically because of pair creation, or particle-antiparticle pair creation, which is happening spontaneously in the vacuum of space pretty much everywhere. If that happens near the event horizon of a black hole, then the net effect is to get a slight leakage of mass and or energy, since mass and energy are interchangeable, and that essentially connotes to a temperature for a black hole. That temperature is tiny. It's I can't remember if it's nanokelvin or femtokelvin. It's an extremely small fraction of a Kelvin, and that's a completely undetectable temperature for any astrophysical object, let alone a black hole, which you can actually see. So detecting Hawking radiation is beyond any observational approach that I'm aware of in the near future. The corollary or connotation of black holes having a temperature and emitting energy is that they're losing mass or evaporating. So black hole evaporation is a consequence of that Hawking-Bekenstein theory. And it is also an extremely subtle and slow effect. A black hole the mass of the sun is going to take trillions upon trillions of years to evaporate. It's actually a number more like trillions of years to evaporate fully. So the rate on a timescale that astronomers can work, like a year or a decade, is completely undetectable. So we would love to be able to test the Hawking-Bekenstein ideas from the 1970s, but at the moment it's simply not possible.
All right, the next question is from Stephen, who is on with us live. What is your view on using entropy as a guide and not a law for understanding the universe's history and potential future?
So entropy is a powerful concept in physics, and it's also related to something that's profound and has philosophical importance, which is the arrow of time. The fact that the universe, as we experience it, the old, cold universe, has a clear arrow of time, that processes on the large scale move forward and yet not backwards. Whereas microscopic physics and all the major fundamental laws of physics are time reversible. You can reverse most particle interactions in time, or you can hypothesize a reverse time direction and you can actually observe that process. So we have a situation in physics where microscopic phenomena are time reversible with very subtle and few exceptions, whereas the macroscopic behavior of the universe seems to move in the direction of higher entropy. So entropy is a profound and important consequence for the universe, or attribute of the universe. The thing that's intriguing about the entropy of the universe, we only have one universe to observe and to live in, so we don't know how surprised we should be by this, is that the entropy of the universe is as small as it is, and was actually smaller at the beginning. So the inflationary idea is based on a kind of space-time that actually has rather low entropy. The entropy of the universe now is essentially governed by the radiation of the microwave background. And in dimensionless entropy units, it's essentially 10 to the power 88. If you play the universe forward in time, and I mean billions of years, when things really start to change because the stars all become dead and galaxies essentially evaporate and supermassive black holes grow in the center of all galaxies, then the entropy becomes even larger, because a black hole, say a black hole the mass of the sun, has an entropy that's 10 billion times higher than the sun itself. So black holes represent extremely high entropy per unit mass form of matter in the universe, and since the universe is tending towards forming black holes, both large and small, the entropy of the universe in the future will be even larger. So the universe as a whole is following the second law of thermodynamics. The entropy was fairly small and actually very small at the time of inflation. It's larger now, and it's going to get yet larger in the future when the stars all die and things evaporate and black holes just eat up everything else and grow. And why that is the case is a bit of a puzzle. And for physicists, the puzzle is why was the entropy of the universe so low at the beginning? Inflation, which was designed to solve some puzzles about the homogeneity and isotropy of the universe, it doesn't actually help. The inflationary idea does not explain why the universe has low entropy at the start. That's essentially put into the theory out of the gate, so it's not an explanation. The fact that the universe did have low entropy, of course, might naturally explain why there is an arrow of time. If the universe had started in a very high entropy situation, chaotic space-time, lots of black holes, for instance, then it might not noticeably evolve over cosmic time, and so there might not be a perceptible arrow of time. So these things, the low entropy of the universe originally, tending higher now, the existence of a time arrow, on macro scales but not micro scales, these things seem to be connected, and we don't know how. There's still some mysteries there.
All right, Mahmoud from over email asks, from where is the Earth gaining capacity to spin around itself for billions of years?
So the Earth was born with a certain amount of angular momentum, which emerged from the protoplanetary disk. So the sun, the disk that collapsed to form the sun, has a certain amount of angular momentum. That angular momentum essentially gets packaged into the planets that nucleate out of that disk. And so the Earth had that angular momentum pretty much at its birth 4.5 billion years ago, and that angular momentum has not really changed. So the Earth is, in a system where there are very few interactions after the planets form, except their continuing orbits. The angular momentum is really not changing. The exception to that for the Earth, of course, is because of its tight coupling to the Moon. So because the Moon is a relatively large satellite, the largest moon of a planet in the solar system relative to the planet size of all, the Earth and the Moon are gravitationally coupled. That explains the tidal locking that leads us to see one face of the Moon, not the whole Moon. And that tidal coupling is also responsible for a transfer of energy between the Earth and the Moon that's leading the Moon to move slowly away from the Earth by about 4 centimeters a year, and the Earth to gradually slow down. So the year is getting very slightly longer. So the angular momentum of the Earth is actually slowing down very slightly due to a transfer to angular momentum of the Moon. The system, the combination of the two, is of course conserved.
Right, the next question is from Roy, who is on with us live. If we assume that the visible universe may accelerate such that we lose sight of the earliest objects, why wouldn't we think that this hasn't happened billions of years ago already?
So it's true that the accelerating universe implies that we will in the future lose sight of things that we can currently see now. So basically we have two transitions that went on. First of all, the universe extremely fast early on, which represents a limit to our vision, because any two points in space were moving away from each other faster than the speed of light for the first third of the universe's existence. So there are clearly regions of space based on that, just the sort of causality of light travel time, which we would not have access to. Dark matter then was dominant, and it was slowing down the acceleration. Slowing down the expansion rate. And that means that if that were all that had happened, that dark matter was slowly decelerating the universal expansion, then gradually we would see those regions that have been wrested from our view by superluminal expansion, they would gradually come into view. And if we were just patient enough, eventually we'd see larger and larger regions of space, more and more galaxies, larger volumes of space-time. But of course, what happened in the last 5 billion years is that the dark energy started to dominate the dynamics of the universe relative to the dark matter, and so the universe has been accelerating. So now we know, since this trend is unlikely to reverse, dark matter will continue to weaken in its effect on the cosmic expansion as the universe thins out, the dark matter thins out, whereas the dark energy is apparently a constant, cosmological constant, and so its accelerating impetus to the universe will just continue unabated, and it will continue to remove things from our view. So we have the bizarre situation where there could have been things that were not available for us to view early on that came within our horizon or were available for us to gather light with telescopes in the middle phase of the universe that might subsequently in the future be taken from our view again because of the cosmic acceleration. So there are things that we've never seen and will never see. There are things that we didn't see early on that came into view and will be taken away from view. And there are some things that were taken away from view that are close enough to us that they will stay within view for quite a while. But the logical endpoint of the cosmic acceleration is that everything eventually will be taken from our view as space-time expands at a faster and faster rate.
The next question is from Victor, who sent it in via email. What kinds of things interact with space-time? For example, could heat from a supernova warp space-time?
So it's a good question of what couples to space-time or what causes changes in space-time. In general relativity, which is a geometric theory of space-time, the curvature of space-time, either globally, speaking of the universe as a whole, or locally, speaking of a particular region where stellar objects or black holes or whatever may exist. The curvature of space-time is related to the density of mass energy. And so space-time is hyphenated because the two are linked through general relativity. And mass energy is hyphenated because it's the sum of the mass and the pure energy, and they're interconvertible, as we know. So in principle, yes, energy from a supernova deposited into regions of space constitute an equivalent mass, and that creates a distortion in space-time. So in the sense that an energy signal through an explosion, like a supernova, propagates through space-time, and it has an equivalent mass, that large amount of energy, then there is a distortion of space-time that's a consequence of that. That's not directly the same as a gravity wave, but you can think of it in the same terms, in fact. So these are very subtle effects because obviously c squared, speed of light squared, is a very large number. So the equivalent mass, even of the energy from a supernova, is quite modest. And that's moving through extremely large volumes of space-time, expanding in a spherical wave. So these are distortions of space-time that are not currently detectable at the moment.
All right, so this question comes in from email. What are the main tasks of astronomers nowadays? Devising observation campaigns, collecting data, simulating, like what do astronomers do?
Yeah, so a good general question about what astronomers do. So professional astronomers, there traditionally were two types of astronomers. There were people who worked with telescopes and observations and data, and people who work with the theories of the universe and the calculations and the math. In fact, most astronomers are trained to be able to do both, because you can't actually be an observational astronomer without being aware of the theories of the objects you're observing. And theorists also have to, even if they don't go observing and use telescopes, they have to know enough about the data and the observations to meaningfully know how to compare theory and observation. But that aside, there is general specialization. So there are a set of astronomers who are trying to test theories, who are trying to make observations into regimes that haven't been tested before, either by working at new wavelengths or with new degrees of sensitivity, or by making time variable observations, or by using a new facility, a new large telescope or something in space that gives them a new capability. And they're going to be doing a combination of two things. They're going to be studying well-known objects to understand them better and to try and nail down their properties. And they're also going to be hoping to discover new things. And the history of astronomy suggests that almost every time you open up a new wavelength or sensitivity regime, you discover things that you didn't predict. So that's the fun of being an observer. Theorists are trying to explain all the things that we see in the universe, and they're kept pretty busy too, because we don't understand everything that we've observed. We've observed dark energy and dark matter that dominate the universe and are not understood, and the theorists are very active in trying to help us develop good physical theories for what these might be. We've just entered the regime of gravity wave detection, and that's obviously a game where the observers are experimental physicists dealing with huge equipment and expensive equipment and in teams of hundreds of scientists. The theorists are also trying to develop ideas for what we might detect in gravity waves. What kind of phenomena lead to gravity waves? So even though theorists and observers specialize, they have to work closely together. And the most productive science in astronomy comes from collaborations between these two groups. Sort of related to the theory group, it's not a third group equal in size, are simulators. That is, people who use computers to simulate things that are maybe too difficult to calculate just because of the complexity of the situation, or just because computers are powerful enough and you can put the physics in the computer, or the astrophysics in the computer, that you can genuinely learn something interesting from that. So simulators, as I'll refer to them, are more related to theorists. They do have to understand the physical theories extremely well enough to put them in a computer and know how to calculate them. But they are also using essentially brute force to do their calculations at a level of detail or in a regime where you simply couldn't do it with pure equations. So simulation astrophysics, or simulations, are a pretty important part of how modern astronomy works. And so these three different groups tend to coexist. It's in a department like mine at the University of Arizona, we have Probably because we have so many telescopes, we probably have a half or more of our faculty are observers of different kinds. Maybe a quarter are theorists, and another close to a quarter are people who work with simulations.
Right, the next question is, Professor, do you have any thoughts on the new starshot program? Do you think you'll have problems with communicating and sending information to Earth, and what are some other challenges?
Breakthrough starshot, which is what the question is about, is this ambitious idea to send nanobots at significant fraction of light speed to Proxima Centauri, to the nearest star system, and send back sensor data on hopefully Earth-like planets in that system. It's an extremely ambitious project, of course, and in a nutshell, it refers to building banks of extremely powerful terawatt lasers on the Earth to beam energy to gram mass micro satellites, if you like, attached to 1 meter solar sails to accelerate them to 5 or 10% of the speed of light, which will get you to the nearest star in a couple of generations. And you need to send lots of them there, of course, waves of them there, because they have to beam back their information back down the chain to get the information to Earth at light speed. This project has been well scrutinized, of course, since they made their public announcement. And people have, the teams themselves, the Breakthrough Starshot, have a website where they list their technical challenges, dozens of them. So they're not shy about admitting that there are plenty of things, plenty of huge technical and engineering hurdles that have to be cleared before they can do this project. And since they've gone public with their announcement, people have weighed in with even more technical obstacles, or perhaps obstacles that they mentioned that some people think they may have underestimated. So it's too early to tell what the consensus view of this project is. The people involved in it are very smart. They're Pete Worden, the head of NASA. There's a NASA Ames head and a lot of technical expertise at NASA that's associated with this, consulting on this. So these people are not naive. They've done difficult things in their careers, but nobody's attempted anything like this. So it's still in the idea churn phase, and I think they wanted to have other smart people commenting and critiquing their ideas. So at the moment, I would say the consensus among the experts is what they propose is not impossible, but it's exceptionally challenging, and probably more challenging than they presented at their press conferences, in the sense that this isn't going to happen in 10 or 15 years. Maybe it'll happen in 40 or 50 years.
The next question is from Suresh via email. So this is regarding the recent detection of gravity waves. Would dark energy have had an effect on the gravity waves that were recently detected? And do you need to take the effects of dark energy into account since they've traveled for billions of years?
In a sense, yeah.
Light years,
in a sense, yes. The effect of dark energy is taken into account because the object that the galaxy, the distant unnamed galaxy where these two massive black holes collided to produce a gravity wave signal, was at a distance of about 1.25 billion light years. And so that the radiation, the gravity wave radiation, was traveling through expanding space-time for 1.25 billion years. And in that period of time, of course, dark energy was accelerating the expansion. And so when the gravity wave theorists take what they would expect the signal to be, the gravity wave signal to be, if you were right up close to two massive black holes colliding, and then you predict how that gravity wave signal will dilute as it travels through three-dimensional space, they also put into that calculation the fact that space-time is expanding at an accelerating rate between when the black holes merged and when we observe them 1.25 billion years later. So yes, the dark energy and its impact on expanding space-time is folded into the calculation of the strength of the gravity wave that you detect. And in the experiment itself, of course, you then reverse that logic to say, we detected a gravity wave of this strength, and the source of that radiation was 1.25 billion light years away. So we infer that at the place that radiation was emitted, it had the appropriate strength to be the merger of two black holes of about 20-odd and 30-odd solar masses. So yes, the dark energy is taken into account.
And then kind of a follow-up question is, where did the energy of the 3 solar masses that was lost when the black holes merged go? What happened to that energy?
That energy was radiated spherically through space-time, and just as part of the signal, basically. Just as in a supernova, a massive star dying, there's a blast wave. There's just a radiation blast wave. There's also a neutrino pulse, something like an Earth mass or a couple of Earth masses of a massive star dying is converted into neutrinos that flee the system at essentially the speed of light. And so that couple of Earth masses from a massive dying star is turned into neutrinos, and that also dilutes and diffuses through space and could in principle be detected. So yeah, all of the energy that's deposited into the universe from these events in various forms is in principle detectable.
All right, so the next question is, how solid is the basis for the age of the universe?
So it's a good question. If you look it up on Wikipedia or wherever your favorite source is, I think you'll see that the age quoted is 13.77 billion years, and the error on that is actually quite small, maybe surprisingly small for a cosmology number. It's, I think, 0.021 billion years. So if you think about that, that's a couple of percent. That's accurate to a couple of percent as a cosmic number. So where does that accuracy actually come from, and can you really believe that? So that age is derived entirely within the context of the expanding universe, the Big Bang model, and it's based on the measurement of the components of the universe, the dark energy, the dark matter, and the normal or baryonic matter, and the current expansion rate, the expansion rate we measure locally. So if you know the local or current expansion rate, and you know the major ingredients of the universe, dark energy, dark matter, and baryonic matter, that affect the expansion rate, then the Big Bang model allows you to back predict when the universe originated. So it's a number that comes from the Big Bang model. And since the Big Bang model provides a wonderful fit, so there's another part of the research on the CMB, the microwave background, is that this Big Bang model with dark matter, dark energy, and baryonic matter fits the exquisite data from the WMAP and Planck satellites. It fits it exceptionally well with basically only 6 parameters. So 6 fundamental parameters of the Big Bang fit an awful lot of data, very, very high quality and precision. So the Big Bang expanding universe model is exceptionally well confirmed by the CMB data. And so our belief in the validity of the age inferred from that model should be very high. The error then comes from taking all the input parameters, the fundamental parameters of the Big Bang, and taking their ranges of variation, their statistical errors and their uncertainties in the fit to the Big Bang model, and seeing what that implies about the uncertainty of the age. So you basically do a very fancy error analysis involving all the variables in the model. And because the model is so well fit by the data, because the data is so exquisite on the microwave background, that uncertainty in the age ends up being very small, like 2%, like 0.021 billion years. And so cosmologists really believe they've measured the age that accurately. Now it would be nice to have a cross-check, and so we do have a couple of cross-checks. The cross-checks come basically from 2 ways of measuring ages that have nothing to do with the Big Bang expanding universe model. One of those is the age of the oldest stars, and so that's based on our understanding of stellar evolution. So we look for old stellar systems, and we model on a Hertzsprung-Russell diagram the place where the main sequence stars turn off the main sequence when the oldest ones exhaust their hydrogen. And that is checked and turned into an age by a stellar evolution model. And the oldest stars in the galaxy, by that reckoning, are about 11 or 12 billion years. Some people even say 13 billion years, but 11 and 12 billion years are the numbers that come out well. And that's reassuring because that puts the Milky Way's age at 1 or 2 billion years less than the Big Bang. And remember, it didn't have to be that way. The stellar evolution model could have said anything. The fact that it says a number that's less than the age inferred from the expanding universe model is reassuring. I mean, it's a cross-check on the model. The other way we can do it, which unfortunately has higher uncertainty, but because it's very direct, is using the decay of radioactive nucleotides. So we can take the longest lived radioactive decays that occur in the universe, typically use of uranium-238 and plutonium-242, and because those decay timescales are billions of years, we can look at the ratios of parent and daughter isotopes, for instance, in solar system material where we measure it directly, and then infer what the initial ratio was, and there you get an inferred age, and it's called cosmochronology, nuclear cosmochronology. And those uncertainties are a little high, as it turns, but they also give numbers in the same regime. They're 10 to 15 billion years, so pretty uncertain, but they're in the right ballpark. So that completely independent method, just based on nuclear physics, pretty much agrees with the model that we have in the Big Bang. So I think all of this lets us trust the fairly accurate number we get out of the Big Bang model.
All right, and kind of follow-up is, he says that recently some supermassive galaxies were discovered that are believed to be too big to have formed so shortly after the Big Bang. So where does that?
Yeah, so it's a good question. So the possible fly in the ointment of the age of the universe comes from a third technique. I maybe should have put it in my list, but it's not a direct cross-check on the Big Bang age. So one other thing you can do, especially with big telescopes like Hubble and the ground-based telescopes, is you can look at the highest redshift or oldest galaxies you can find in the universe, and then try and measure the age of their stars. So if you find a galaxy at a redshift of, say, 10, which is very far in the universe, when the universe, that light is being seen when the universe was only 500 million years old, roughly, and you can show that the oldest stars in that distant galaxy or 2 billion years old, then you have a problem, because you've got something that so should have only had 500 million years after the Big Bang to form its stars, and you're saying it has stars that are 2 billion years old in it. So that's another pressure point or cross-check on the Big Bang model. And I would say pretty much every year or so there's a news release or a research article that implies some kind of a problem where there isn't enough time in the young universe to form a galaxy that large, or that the stars in that galaxy are too old, or fill in the blank. And there has been one of those in the last few months. So far, none of those have held up at the level of providing a serious challenge to the Big Bang age. And that's typically because we simply don't know how long it takes for a massive galaxy to form. For instance, people look for quasars or supermassive black holes in the early universe, and we found black holes about 1 billion times the mass of the sun that exist apparently within roughly 500 million years of the Big Bang, and people said that couldn't happen either, that they have to be older than 500 million years. You can't get a 1 billion solar mass black hole that quickly. But it turned out when people did better modeling that you actually could get a 1 billion solar mass black hole. It's not that likely, it shouldn't happen very often at all, but it can happen. So I would say these research results are intriguing, but they're not yet at the level of validation, or the knowledge is not that secure, the inference is not that tight that you could use them to argue against the Big Bang or the age from the Big Bang model.
The next question is from Will, who asks, what is the benefit of having two telescopes together, like Keck on Mauna Kea, or I'll insert like the LBT here in southern Arizona? And is it for 3D images? And if so, why is that important?
Both of those cases, and all the cases we have where there are multiple telescopes that are of the same design and the same size, the VLT, the European Southern Observatory VLT in Chile is another example. Those are projects where the telescopes, probably for most of the time and certainly early on, were designed to be used separately and independently. So the two Keck telescopes for most of their time are operating as two 10-meter telescopes independently, pointing at different objects. They often even have different type instruments on them at the same time. And they are doing separate science essentially. But right from the start, they were built with the possibility of having their radiation combined in a vacuum chamber underground to make an interferometer. And so the Keck telescopes were built on top of Mauna Kea with a tunnel underneath right from the time they were built, even though it took a decade or so for the engineering to work and start to be used, because the goal was to combine their light coherently, meaning they would be pointing at the same object, and we'd be mocking up a telescope of the size of the distance between the two Kecks, which is about 50 meters, which of course is incredible angular resolution. Now, the LBT in Arizona is more overtly done to do that, because the LBT is two 8.4-meter mirrors in a common mount. They're sort of on a yoke that has them pointing in the same place. And that telescope was clearly designed right from the start to combine those light beams and do interferometry between them. The VLT in Chile is the same thing, though for most of its history, those four telescopes just operate independently and they each do different science. But increasingly in the last 5 to 6 years, they've been used in harness to do interferometry. So the advantage of interferometry, and the reason you would do this, is of course you get incredible angular resolution. Your angular resolution goes up or improves with the size of the baseline between the telescopes. And it's as if you had an optical or infrared telescope that was the size of the distance between the most disparate elements. And that's an incredible advantage.
All right, the next question is from David, who asks, are lunar eclipses more frequent than solar eclipses, or the opposite?
So the lunar eclipses are much more frequent than solar eclipses. And the reason is fairly simple in terms of the geometry. So remember that the solar eclipse is when the moon comes between the sun and the earth, and because the sun is 400 times bigger than the moon but 400 times further away, they make the same angle in the sky, about half a degree. And so when the moon passes directly in front of the sun, it blots out the sun, and so that's quite a dramatic effect. But of course, because the shadow of the moon cast by the sun is a very small shadow, typically 5 or 10 miles across, that event is only seen on very small parts of the Earth, and of course it moves across the Earth's surface at the rate that the Earth is spinning. So solar eclipses are rare events because the shadow is so small. Well, they're rare because the alignment doesn't happen perfectly very often, because the moon's orbit is tilted a few degrees with respect to the Earth-Sun orbit. That's the first reason they're rare. The second reason they're rare operationally is that the shadow is small, so you have to either happen to be at the right place on the Earth's surface or travel there. And the third thing is that they don't last very long because the Earth is spinning. And so the typical duration of totality of a solar eclipse is a couple of minutes. The one that I went to in Indonesia was basically 2 minutes, and the longest one I've ever seen, and pretty much the longest one at all, was in 1991 in Baja, and that was about 6.5 minutes. They don't get much longer than that. On the other hand, a lunar eclipse is a much more favorable geometry as far as being able to see it, or the frequency of it. The issue of the Sun-Earth-Moon alignment is the same, because the moon's tilt means that we don't see a lunar eclipse every month, as we would if the Earth, Sun, and Moon were all perfectly in the same plane. So none of these things happen as often as they would if everything was in the same plane. But of course, the lunar eclipse is the Earth casting a shadow on the moon, and since the Earth is a much bigger object than the moon, that shadow covers the moon and means that the Earth's shadow can be seen by anyone on the night side of the Earth at that time. So you don't have to be in a small little patch of the Earth's surface to be lucky enough to see it. You can be anywhere on the night side of the Earth as that shadow is cast over the moon. As the moon passes through the Earth's shadow, of course, the moon is smaller than the shadow, and so that lasts for a while. So you have at least an hour or so of eclipse, not total eclipse for that long, but you have an hour and a half of partial eclipse. So you have something that's visible if they looked to roughly half the people on the Earth, and it lasts for a lot longer, and it happens more frequently. So lunar eclipses maybe not less special because of that, but they're much more frequent.
The next question is from Stephen, who is on with us live, who asks, the speed of the starshot is planned to be 15% the speed of light. At what percent of the speed of light are the effects of general relativity time dilation significant? Yeah,
that's ambitious. I mean, I've read 5, 10, 15%. So they're hoping to get to 15% of the speed of light. And remember, they're having to do this with solar sails and pulsed energy from terrestrial lasers. So if you think about it, all of the acceleration has to happen in an incredible impulse. So those solar sails have to get an incredible kick while they're still near the Earth. So they're going to have to reach that incredible speed really quite close to the Earth, because the beam, however tightly you collimate the laser beam, it's going to defocus through space, and so you lose your push. So that's their huge technical challenge, is getting enough of a kick from these focused lasers to get that acceleration up to that very high speed. As for the relativity question, the Lorentz factor, which is the main factor that relates to time dilation, in the sense that the time in the observed frame equals the time in the rest frame times the Lorentz factor. Lorentz factor is the square root of 1 minus v squared over c squared. So you can just plug it in. I probably can't do it very well in my head, but if you're talking about 15% of the speed of light, then v over c is 0.15, and 0.15 squared is 0.2 roughly. So you have something like a 20% time dilation from that situation. So yes, there is time dilation, and the effects of special relativity are going to be manifest in that, but not extreme effects.
All right, the next question is from Wen, who is on with us live. Could you explain what the difference is between matter and particles?
So matter is in colloquial speaking, matter just means stuff. I mean, it's just objects made of, solid, liquid, gas, or perhaps plasma. That's matter, and it's a sort of large-scale definition of property. Particle sort of relates to what the matter is made of. It's referring to the more fundamental constituents. So when we talk about matter, again, it can be those various forms, solid, liquid, gas, without paying attention to what that's made of. In other words, in terrestrial material, those components obviously could be atoms or molecules, or they could be, compounds or aggregates. So this is sort of gross chemical properties. When people talk about particle, they're really talking about the fundamental constituents. So they're now asking more like, is this made of protons and electrons, or neutrons, or some other form of subatomic particle? So it's the question of looking at it from this perspective of fundamental constituents, or just the aggregate properties.
Right. The next question is from, Robert. Can you discuss the shape of the universe being flat versus spherical or another shape?
So if you go to the formalism of general relativity, the theory that describes gravity in geometric terms, the solution of the equations of general relativity involve a numerical term. When you form the metric, which is essentially this geometric description of space-time, there's a factor in front of it that has a number called k, and k can either be +1, 0, or -1, three possible solutions to those equations of general relativity. K of +1 represents positive space curvature, like the surface of a sphere in 2 dimensions. K equals 0 represents flat space, like Euclidean space, just a tabletop or a sheet. And then k equals -1 represents negative space curvature, which in 2 dimensions would be hyperbolic, or like the surface of a saddle extending infinitely in 2 dimensions. So those are the 3 possible curvatures space can have, one of which, of course, is no curvature at all, just Euclidean space. So that's what general relativity accommodates, essentially, positive, negative, or 0, and any amount of positive or negative that you want, more and more extreme. The universe we live in has been measured, its curvature has been measured by the microwave satellites, because they're looking at radiation very close to the time of the Big Bang, and that radiation has filtered through and traveled through the universe, propagating at light speed for 13 billion years. And so we can see, in terms of the characteristic size, angular size of features of the microwave radiation, whether those characteristic features have either amplified, de-amplified, or not changed in angular size over 13 billion years and over traveling across that enormous amount of space-time. And the answer is they haven't magnified or demagnified relative to a model of the expanding universe. So the microwave background data shows that the curvature of the universe is very close to 0. And so space is flat in 3 dimensions, and it's flat within about 1 or 2%. It's actually a fairly precise measurement of the microwave background. So although general relativity allows the universe to be curved, positive or negatively, and that's part of the theory that space-time can do that. The universe we live in seems to be, or the part of the universe we can observe with our telescopes, which is pretty large, it's 40 billion light years in any direction, seems to be spatially flat.
All right, the next question, I think this will have to be our last question for the day, is from Wen, who is on with us live, who asks, could gamma rays be detected on the mountain in Chile?
Yes, there are gamma ray detectors. We have a gamma ray detector, the Whipple Observatory here in southern Arizona. Those gamma ray detection is, of course, best done in space, and so probably the premier gamma ray telescope was the Compton Gamma Ray Observatory of NASA, which did its work for pretty much 2 decades in the 1990s and the 2000s. You can detect gamma rays from the ground, although they don't penetrate the Earth's atmosphere, because gamma rays hitting the top of the Earth's atmosphere produce air showers. They essentially produce cascades of high energy particle collisions and interactions, and so the byproducts of those collisions, those byproducts of the initial interaction of the gamma ray that can be detected, the air shower can be detected on the surface of the Earth. The higher altitude, the better, the cleaner that signal, and so northern Chile, the Atacama Desert, and very high regions around the Atacama are favored places to do that kind of science, and there are several small gamma ray observatories in the Atacama Desert. And they are returning very valuable information because we don't currently have a large gamma ray observatory in space. So pretty much at the moment, that's the only way to do that science. So thanks very much. Appreciate your questions. Really good questions as always. And we'll be back doing this probably at the very beginning of July.